We can start now.
Thank you. Let's start. Today, I would like to discuss some issues on the local geometry of spherical varieties. So I will retain my usual notation. X will be a spherical G variety. With the open orbit Y0, which is a spherical homogeneous space. And by Y, I will denote any G orbit in X. As usual. Recall that we have associated to any G orbit an open B-stable subset in X called the open B chart, which I denote by X sub Y0. Which is obtained from X by removing all B-stable prime divisors not containing Y. So this open B chart intersects Y, and it is an affine open B-stable subvariety, as we proved before. By the way, note that X is covered by the shifts of B charts applying elements with shifts by elements of G over all G orbits in X and elements G small in G. Because any G orbit intersects some B chart, and therefore the shifts of this B chart cover this orbit. And of course, we may choose a finite subcover of this open affine subsets. By Noetherian property of the Zariski topology. If we are interested in local geometry of my spherical variety X, it suffices to focus on a single B chart, on an arbitrary B chart. So the question I would like to address now is, what is the geometric structure of a B chart, of a given B chart corresponding to a given G orbit in X? To this end, let me introduce a subgroup, which I denote by P, or P sub Y, to emphasize its dependence on Y. It consists of all elements of G, which preserve the B chart X, Y naught. This is a parabolic subgroup of G containing the Borel subgroup. Because if G is in the Borel subgroup, then of course G preserves the open B chart because the open B chart is B stable. So we have this parabolic subgroup, and also this parabolic subgroup can be defined as the subgroup consisting of all elements of G, preserving, maybe let me shift it to The next line. This parabolic subgroup consists of all elements of G, preserving each B-stable prime divisor, which does not contain Y. Because these B-stable prime divisors not containing Y are exactly the complementary divisors to this affine open B chart. We remove these divisors to obtain the open B chart intersecting Y, the canonical open B chart intersecting Y. What can this parabolic subgroup P do? It can permute this irreducible component of the irreducible components of the open B chart. Yes. Yes.
Well, I forgot why is X covered by the translation? Oh, why?
Well, because for any G orbit, we have a B chart intersecting this G orbit. And since this B chart intersects Y, the shifts of this B chart contain Y, because Y is a single G orbit. Okay?
I mean, why there is why every G orbit intersects X, Y naught? I mean this.
No. I mean not every G orbit intersects X, Y naught. The point is that for any G orbit there exists a B chart intersecting it.
Yes.
Just by definition. So here
so we do not. We should enumerate every Y. Oh, not
exactly.
Only
As I write here, over all Y, we take the B charts and their shifts over all Y and all G. Okay. I hope it is clear now. Now let me come back to this line. This parabolic subgroup P preserves the open B chart and may only permute the irreducible components of the complement, which are these divisors D. But it is well known that each parabolic subgroup is connected. So it cannot permute the irreducible components of the complement of the B chart. It has to preserve them all. So this condition has to be satisfied. So this parabolic subgroup is the common stabilizer.
So if G permutes but not keep the divisor, then it is local locally in the group G, and the element G should also preserve.
Well, but the point is that P is connected. Any parabolic subgroup is connected.
I know. P is connected and P is locally acting on the divisor the same. I see.
Yeah, so a connected algebraic group acting on some set of subvarieties, finite set of subvarieties, cannot permute them because it is connected. I mean. Well, so we have this parabolic subgroup, and the structure of parabolic subgroups is actually well known. I can give you a reference, for instance, a reference on parabolic subgroups and their structure. Reference on parabolic subgroups. For a reference, you may take, for instance, the book of Humphrey, which I cite many times as one of standard references in algebraic groups, the book of Humphrey, linear algebraic groups, section 30. It is about parabolic subgroups. Of course, other textbooks in the theory of algebraic groups also suit. What I need from the structure of parabolic subgroups, I need the Levy decomposition. So Levy decomposition is the following. The parabolic subgroup P can be decomposed as a semi-direct product of a normal unipotent subgroup P sub U and a reductive subgroup L. So this normal unipotent subgroup is called the unipotent radical. It is the largest normal unipotent subgroup in P, and this L is reductive. It is called the Levy subgroup.
Unipotent radical or unit?
Unipotent, yes, unipotent radical.
Oh, this group is the largest unipotent group in P,
Largest normal unipotent subgroup.
Normal. So
Yeah.
there may be larger non-normal unipotent subgroup.
Exactly. Yes. So, and this Levy subgroup can be chosen in such a way that it contains the maximal torus, which we have chosen, contained in B. So we may assume that L contains the maximal torus T. And in this case, this L is unique. And it can be decomposed as a product of its derived subgroup, the commutator subgroup, and this torus T.
Professor.
Yes.
Well, the reductive group, the reductive group L is connected. Oh yes.
Yes. It is connected because P is connected. Otherwise, P would be disconnected.
So how can L? So I think L must contain a maximal torus. I mean.
Well, L is defined uniquely only up to conjugation. But if we choose L to contain a given maximal torus, so T is fixed.
So we
given maximal torus. In this case, this L is unique. And it is decomposed in this way, so that the derived subgroup is semi-simple. L is reductive, but the derived subgroup is semi-simple. This is standard facts from algebraic group theory, which can be found in Humphrey's book and in other books. So I will not prove them, but I will give you an example just for you to see how things look like. So, for example, let's take for G our standard example of a reductive group, GLN. And for B, our standard Borel subgroup in GLN, that is the group of upper triangular matrices, like this. So upper triangular matrices. So we have something here, something on the diagonal, and zeros below diagonal. Then any parabolic subgroup containing B actually consists of blockwise upper triangular matrices with some sizes of blocks. So any parabolic subgroup is of the following form.
Hey, Professor, sorry
yes.
to bother you. Well, the decomposition of L, the multiplication of L is the multiplication in the group, right? Not direct.
Of course, it is not a direct product. It is a multiplication in the group. But this, I mean, yes, you are right. The first factor in this product is normal, of course, because it is a derived subgroup. But T is, of course, not normal in L, so it is not a direct product. Yes. Well, so as I said, any parabolic subgroup in containing upper triangular matrices is actually the group of the form. It consists of blockwise 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 upper triangular matrices, so it looks like this. So we have this block structure like this. I don't know, maybe here, and then here, and we take here, here. So we have, let me draw it better a bit. Maybe like this. So we have zeros here. And we have something on the diagonal blocks and above. Of course, the matrices in the group should be non-degenerate, so the non-degenerate condition is imposed on diagonal blocks. The block structure is fixed. The sizes of blocks are fixed. And all matrices of this form with fixed sizes of blocks, so there may be more than 3 blocks, less or more than 3 blocks, it is just an example. All matrices of this form suit. So any parabolic subgroup containing B is of this form, okay? And the Levy decomposition looks as follows. So let me just copy this picture. For the unipotent radical, we have the following condition. So the diagonal blocks should be identity matrices. So we have an identity matrix here, here, and here. And we may have anything above the block diagonal. So this part is arbitrary.
So PU is even smaller than the unipotent group, right?
PU is smaller than the maximal unipotent subgroup in B. Yes, yes. Because the maximal unipotent subgroup is non-normal, non-normal in P. It is normal in B, but it is non-normal in P. And PU is the maximal normal unipotent subgroup. So this is the shape of the unipotent radical. And the Levy subgroup, well, as you guess, the Levy subgroup is something complementary to the unipotent radical. So we get the following. So the Levy subgroup, let me put it here. The Levy subgroup is of the following form. We have zeros above the diagonal, not only below, but also above the block diagonal. And on the block diagonal, we have anything non-degenerate, any arbitrary non-degenerate matrices. So here, here, here.
It is a block diagonal matrix.
Exactly. Block diagonal matrices. Here, here, and here. We may have anything non-degenerate because we are in a group. If we turn to the Lie algebra, then of course the non-degenerate condition may be waived. But on the group level, we have anything non-degenerate here. You see clearly that this Levy subgroup of block diagonal matrices contains the maximal torus T, consisting of usual diagonal matrices. And the derived subgroup of L is given by the condition that the determinants of all blocks are equal to 1. So we have this blocks, diagonal blocks. This one, and this one. And the condition for the defining the derived subgroup, the commutator subgroup, is that the determinants of all these blocks should be equal, of each of these blocks should be equal to 1. So these are the equations, the defining equations for the derived subgroup of L. This is an example of the Levy decomposition of a parabolic subgroup in GLN.
Hey, Professor.
Yeah.
The determinant 1 only ensures that this group is contained. The derived subgroup is contained in the determinant 1 block diagonal.
Of course. No. I mean the derived subgroup consists. These are defining equations. So the derived subgroup consists exactly of all block diagonal matrices with determinants of blocks equal to 1.
Oh, so this is non-trivial.
Well, it is a computation because it suffices to prove it for a single block, because this L is a product of GLKs where Ks are sizes of blocks. So the derived subgroup of a product group is the product of derived subgroups of factors. So it suffices to prove this for a single block. And it is well known that the derived subgroup of GLN is SLN or GLK, if you like. Okay?
Oh, derived. Oh, yes, the derived of GLN is SLN. Oh, I see.
Okay. So the following theorem, which I'm ready now to formulate, describes the structure of the open B chart, and it is known as the local structure theorem. Maybe I should formulate it on the next page because it takes space. So the local structure theorem goes back to Brion, Luna, and Wust. You have already seen these names. This is in their paper of 1986. The theorem states the following. So I retain the previous notation. So we have the spherical variety X, we have a G orbit Y, and we have the canonical open B chart X, Y naught. The theorem states that there exists a closed L stable subvariety Z in the open B chart in here, such that
closed in X or closed in the B chart?
Closed in X, Y naught.
Oh, in the B
not
chart.
in X. Yeah. Closed in here. Such that the following holds. So first, this Z is an affine spherical L variety. So it is spherical for the action of L, not for the action of G. It is not stable under G. With the unique closed orbit, we know that an affine spherical variety is simple. It contains a unique closed orbit. So the closed orbit in Z with closed L orbit, the closed orbit in Z is exactly the intersection of the orbit Y with Z. So this is the first statement. yeah, maybe let this be the second statement. So the first statement, yeah, I'm sorry, I will shift it. I will shift it to some next line. So the first statement,
Is this Z unique?
No, it is not unique. Well, it is essentially unique. I mean, it is unique to up to an isomorphism, but it is not unique literally. So the first property, the first statement is that the whole B chart X Y naught is obtained from the Z by the action of P. So you spread the Z by the action of P, and you obtain the whole XY naught. And moreover, this open B chart is isomorphic to the homogeneous bundle, homogeneous fiber bundle, P cross L Z. So this means, I recall the notation, this means that this is a fiber bundle over P mod L, of the homogeneous space P mod L with fiber Z. Okay? And by the Levy decomposition, which we have here, we can also write this fiber product in the following way. Not fiber product, but homogeneous bundle in the following way. It is isomorphic just to a direct product of the unipotent radical of P cross Z. Okay? So the picture is as follows. Let me draw a picture for you. This I will shift to the bottom. The picture is as follows. So we have this open B chart X. Let it be like this. I don't know. This is the open B chart. Inside, this open B chart, X, Y naught, is fibered over homogeneous space P over L, which is isomorphic to just to PU because of the Levy decomposition. This is a fiber bundle. Let me denote it by phi. And Z is a fiber of this fiber bundle. So we have Z. It is a fiber over a point whose stabilizer is L. And the group PU acts simply transitively on this homogeneous space. And this action is compatible with the action on above, so that the PU orbits intersect transversally this Z. The PU orbits intersect this Z transversally. Okay, so the picture is something like this. These are PU orbits. Okay, so this shows the direct product structure of this open B chart. And this Z, this subvariety Z, is called a Brion-Lunavu slice. For short, we'll write it as BLV slice. It is a cross-section for the PU orbits in the open B chart. Brion-Lunavu slice. Sometimes we'll drop this abbreviation and we'll call it just a slice. Okay, so this is the first statement. The second statement is, which I already wrote here, that the Z itself is an affine spherical variety for the action of L, And the closed orbit is just the intersection of the closed orbit y of the orbit y with z.
So this is a simple spherical variety, right?
Yeah, z is simple. X is not necessarily simple, but z is simple because it is affine. Yeah. And the third property.
Well, I think affine is not equivalent to simple. I mean,
not equivalent, but affine implies simple. We have proved that before.
Oh, I remember wrongly.
Yeah. We have proved that before. Yeah. The third property, the third statement says that the color data of this orbit y and this affine spherical L variety z are essentially the same. That means, first, that the weight lattice of z is the same as the weight lattice of x. Secondly, the cone in the dual vector space, in the space spanned by the dual weight lattice, the cone corresponding to the closed orbit y intersect with z coincides with the cone corresponding to the orbit y. And also, the set of colors in z containing the closed orbit y intersect with z, this is the set of colors in z, can be naturally identified with the set of colors on x containing the orbit y, such that they are not stable under the parabolic p. So the weight lattices are the same, the cones are the same, and the set of colors may become smaller. We do not take all colors in here, we take only those colors which are not stabilized by p, by this parabolic subgroup p. But essentially, the color data of z are recovered from the color data of x in the neighborhood of y. That is the colored cone corresponding to this orbit y. This is the statement of the local structure theorem. Now I want to turn to its proof. If there are no questions on the formulation, on the statement, then I would like to turn to the proof.
So the color is the divisor that is not fixed by the whole p, right?
Yes. Colors, by definition, colors are fixed by b, stabilized by b. They are not pointwise fixed, but they are fixed as a whole. They are preserved by b because they are b-stable divisors. But the requirement is that they should not be stabilized by the bigger subgroup p. Only those colors will correspond to colors on z. Okay? Well, so this is the statement of the local structure theorem. And now I would like to turn to the proof. First of all, we may assume that x is simple. With the unique closed orbit y. This is because we are interested in the structure of a B chart, and B chart is already contained in x sub y. If we take the union of those orbits in x which contain y, then this will be a simple open subvariety containing y, and the B chart is contained in it. So we may shrink x and replace it with this guy, because we are only interested on what happens on the B chart. So we may assume that x is simple. Now, the complement of the open B chart, if x is simple under this assumption, the complement of the open B chart is the union of all colors which do not contain y. So D runs over those colors which do not contain y. Okay? this is the complement on the open B chart. Maybe I will move this here. Okay. And let me observe that these colors in this union do not contain any G orbit on X. This is because they do not contain the closed orbit. But if they contained any other G orbit, then they would contain the closure of this G orbit, which contains in turn the closed orbit. And they do not contain the closed orbit. So these colors do not contain any G orbit. By a lemma which we proved earlier, some time ago, this implies that each of these divisors D is Cartier. And the sum of all these divisors is also Cartier. So this implies that the divisor delta, I will denote it by delta, which is the sum of all these D's. So D runs over the set of colors minus those containing Y. The sum of all of these divisors, maybe with some multiple, I will take a multiple M, a positive multiple M, sufficiently big.
So why is the union of D does not contain G orbit?
Because, let me repeat, because if not only the union of D, any D does not contain G orbit. And the union of D does not contain G orbits because any D does not. So G orbits are connected, yeah, and irreducible.
G orbits are connected, and every D is not stabilized by G, so any D is does not contain a whole G orbit.
No, this is not about stabilizing anything. This is because so any G orbit is connected, and if a G orbit is contained in the union of D's, because it is connected, it should be contained in some of these, in one of these. But no D, no one of these D's contains a G orbit. This is because they do not contain the closed orbit. If D contains,
I think we can use the fact that D is not stabilized. D is not G stable.
Well, D is not G stable, of course, because D is a color. By definition, color is not G stable.
So we can conclude that D does. Oh no, D may still have G orbit. So
in principle, colors may contain G orbits. But if a color contains a G orbit, then it will contain the closed G orbit. This Y, because it is unique. Y is a unique closed orbit in X. We now assume that X is simple. But we removed, here we removed those colors which contain Y. So the remaining colors do not contain Y, and therefore they do not contain any other G orbit. Okay? Okay, so now this divisor is Cartier. And since it is Cartier, we may consider the respective line bundle on X. And this delta is the divisor of a canonical section of this line bundle. So this delta is the divisor of some, S, where S is a section of the line bundle associated with this divisor. And also, since this divisor, delta is in the complement of the open B chart, it is stable under P. So delta is P stable. This is because, because P stabilizes all divisors in the complement of the open B chart, because of this. So delta is, let me write it here. So delta is P stable. And therefore, this section S, whose divisor is delta, is P semi-invariant. P semi-invariant of some weight, of some eigenweight lambda. So this is the picture.
So we should have sufficiently large M to make this Cartier.
Yeah, no, not to make this divisor Cartier, but to make the group G act on the respective line bundle. You may recall that.
Yes, I recall that.
Okay,
So why is delta P stable? I mean,
because each of these D's is P stable.
Oh yes, the definition of P is. Yes, I see.
Okay, very good. So let me move it somewhere here to make it more clear. Okay. Yeah. So we have this picture like this. And now consider the following rational map. Consider the rational map. I will denote it by phi. It will be actually the phi which is in the formulation of the theorem, but so far we don't know it. Consider the map phi from X to the dual of the Lie algebra of G to G German, small German star. It is a rational map defined as follows. So phi of X should be a point in here that is a linear function on G. And this linear function is defined as follows. So the pairing of this phi of X with any element in G is by definition the following. So you consider the section S, this canonical section S. You apply this element psi to this section. Let me comment. This section S belongs to the space of sections of this line bundle. This space of sections is a G module. G acts on here. G has a linear representation in the space of sections. And therefore, the Lie algebra of G also acts on here. And we may apply this element of the Lie algebra to S. So we have this section. This is another section of the same line bundle. We compute the value of this section at the point X, and we divide it by the value of the section S itself at the point X. Since these are the values of sections of one and the same line bundle at one and the same point, their ratio is a scalar. So we get a scalar, and therefore this guy is a linear function depending on psi, yeah? A linear function in psi. So if we take this for any psi.
What is Y?
In G, what is what?
Oh, this is G. Oh, the Lie algebra of G.
Yeah, this is the Lie algebra. This is not Y. This is the Lie algebra of G. This is small German G. Maybe I didn't write it clearly, but it is the Lie algebra of G. Yeah. So this formula defines a linear function on G, and if you take this for any X, this gives you a map, a rational map, because the denominator here may vanish. This map is not everywhere defined. However, this map has the following properties. So first of all, this map is P equivariant. P equivariant. Well, this easily follows from that S is a P semi-invariant section, but let me leave it to you as an exercise to check. It is just straightforward checking, but I don't want to spend time on it. So as an exercise for you, let me put it in red, as I usually do. As an exercise for you, I'll leave to prove this, to check this.
To check phi is P equivariant, right?
Yes, phi is P equivariant, commutes with the action on P, on here and on here. On here we have the co-adjoint action, and on here we have the given action. And also,
well, how
yes.
is Lie algebra acting on S?
Let me repeat, because this space of sections is a G module. The group G acts here.
Yes.
It is a linear representation of G. And when you have a linear representation of G, you take its differential and you get a linear representation of the Lie algebra of G.
Oh, I see.
So you may apply elements of the Lie algebra to the vectors in this space. Okay?
Yes.
This makes sense. So this formula makes sense. Okay. And the second property is obvious. The map phi is regular. In general, it is rational, but is regular on the open B chart. Because the open B chart is exactly the non-vanishing locus of S by the construction of S. So on the open B chart, this denominator doesn't vanish, and this formula gives you an everywhere defined map. Okay. Now we want to identify the image of the open B chart under this map phi. First, so now there is a sort of digression. So first, we can identify the dual of the Lie algebra with the Lie algebra itself via an invariant non-degenerate inner product. On the Lie algebra G, we have an inner product defined as follows. We may define an inner product as follows. So the inner product of psi with eta can be defined as the trace of the product of psi and eta in the usual sense if we consider them as linear operators on some vector space. So to this end, we can embed G in some GLM. Any algebraic group can be embedded in some GLM.
Invariant
and therefore,
inner product. What invariant?
I will comment in a minute. So if G is embedded in some GLM, then small g is of course embedded in the Lie algebra of GLM, in the Lie algebra of all n by n matrices. And we can consider the elements of the Lie algebra G as matrices or as linear operators, if you like, and we can take the trace of their product. And this gives you a bilinear symmetric form on G, symmetric bilinear form, which is the inner product I want to define. This product is invariant in the sense that when you act on psi and eta by the adjoint action of G, invariant with respect to the adjoint action of G. When you act on psi and eta with the adjoint action by the adjoint action of G.
We actually on the both, right?
On the both, yes, on the both. When you act by the adjoint action, then the product will not change.
So this is why we did not use a transpose in the inner product.
No. We may use transpose. This will give you yet another inner product, but I don't want to do it. Yeah. We define like this.
But will this product will just I mean, this is no inner product because the result may not be a positive real number. I mean.
Let me recall that we are working over an algebraically closed base field. So of course, no real numbers. The base field is algebraically closed. The inner product, in my sense, is not the Euclidean inner product, which you are used to.
Well, so this is just
a symmetric bilinear form.
Bilinear form, non-degenerate symmetric.
Yes, and the point is that it is non-degenerate. It is non-degenerate because G is reductive.
Oh, so this is the some basic theorem of fundamental group theory, right?
Yes. This is a property, a non-trivial property of reductive groups. But let me give you a reference. I don't want to prove this property, of course, because it is beyond the scope of my course. But let me give you a reference. Maybe I can put it here. For instance, you may look in the book of Onishik and Winberg, which I also quoted before, Onishik and Winberg. Which is, the title is Lie groups and algebraic groups. I gave you a list of reference, so this is in this list. And these inner products on reductive or semi-simple Lie algebras, as a particular case, are discussed in chapter 4 and paragraph 1 of this chapter, section 1 of this chapter. Okay, so this is a reference. For the sequel, to conclude the proof, I need some properties of this inner product, but this I will discuss after the break. Now it is time to make a break, so let's do it. And still, if you have questions, then I'm ready to answer, as usual.
So the non-degenerate condition is necessary. Is it sufficient?
Sufficient for what?
For G to be reductive.
Yes, actually, this is a criterion. So if you have the picture of this kind, so if an algebraic group G is embedded in some GLN, which gives you an embedding of the Lie algebra in the Lie algebra of GLN, then it is for G to be reductive, it is necessary and sufficient that this product is non-degenerate.
So we have an embedding of G in GLN, right?
Yes.
But I mean, so this way there is no when we define the inner product, we did not use anything about the section space. I see.
No. This is this is a digression. You may forget. So when we discuss these things, you may forget about what was before. You just consider a reductive algebraic group and its Lie algebra and so on. So this is a kind of digression, but I need this digression to proceed with the proof. So maybe I would put it like this to make the proof more structured. This is the first step, and this is the second step, which is a digression. Okay. More questions? There is something in the chat, but this is in Chinese, so there are no questions, I guess. Well, we still have some 6 minutes of the break, so if you have more questions, then just ask. But for the moment, I will turn off my microphone. Well, let's continue. So we have introduced an invariant inner product on the Lie algebra of my reductive group. And let me mention a couple of properties of this inner product. First, the inner product which we defined is non-degenerate also on the Lie algebra of T. This is just because T is also reductive. And secondly,
what T? The maximal torus, or
yes, T is the maximal torus in G. And this German T, small German T, is the Lie algebra of T. Okay? Again, we already used this notation before, so nothing new for us. And the second property is that if we consider the product between two root subspaces, say G sub alpha and G sub beta, these are root subspaces corresponding to the roots alpha and beta, then this product is almost always zero. It is zero unless beta equals minus alpha. This is because the invariance property, because when you act by T on the left argument and the right argument of this inner product, if you act by T, then here it will be multiplied by alpha, and here it will be multiplied by beta. And in general, the inner product should be preserved. If it is non-zero, then the value should be preserved. So the product of alpha and beta should be equal to 1. In the additive notation, this means that beta equals minus alpha. This is the only case in which this product can be non-zero. In all other cases, this product is zero. And also, of course, more or less for the same reason, also the product of T, of the Lie algebra of T, with any of the root subspaces is also zero. These are main properties of this inner product. And now let's come back to our situation. So this will be the third.
Professor, sorry.
Yeah.
So this alpha is well, the index alpha is a one dimension. No.
Yes. These guys are one-dimensional root subspaces in G.
I mean, alpha is a one-dimensional representation of G, right?
It is not a one-dimensional representation of G. It is a one-dimensional representation of T. It is a root subspace. It is an eigenspace for the action of T in the Lie algebra of G.
Oh, the action of T.
Yeah. Just recall the root decomposition of the Lie algebra of G. We have discussed the root decomposition at some first lectures of this lecture course. I don't remember when, but we did it. So
sorry.
Yeah.
So what will happen if alpha equals to beta?
Then this pairing is non-zero, because otherwise, if this pairing also will be zero, then this G alpha will be in the kernel of the pairing. But the pairing is non-degenerate; it has no kernel.
So maybe beta not equals to alpha or minus alpha. Right?
Yes, the pairing of G alpha with G minus alpha is non-zero. The inner product between these two root subspaces is non-zero. Okay. So now let's turn back to our situation. This is the third stage, the third step.
So Professor, we can the last equality, in the last equality we can see the small t as the eigenspace correspond to 0, right?
Exactly. So as I said, the reason for this property is the same as here. Exactly, you are right. Absolutely. Okay. Well, so coming back to our situation, to our proof, let's recall that we have this eigenweight lambda for the canonical section corresponding to this divisor delta, to this p-stable divisor delta, which is the sum of all colors in the complement of the open B chart. Okay, and this lambda is a weight. It can be viewed as a linear function on T, on the Lie algebra of T, because it is a weight. And this guy is identified by the inner product with the Lie algebra of T itself. Yeah. Now, the structure of the Lie algebra of the parabolic P, so this small German P denotes the Lie algebra of big P, the Lie algebra of our parabolic, is in fact the following. So it is the direct sum of the Lie algebra of T and of those root subspaces G alpha, which correspond to the roots whose inner product with lambda is non-negative. I should comment on this latter condition because here we speak about inner product of weights. Weights can be viewed as elements in T star, but we can identify T star with T having a non-degenerate inner product on T. So by this identification,
sorry,
yes?
Sorry, Professor, I have a question. So
yeah, please.
So the bilinear form, well, by the same argument, if beta equals to alpha, then the invariant case still tell us that their inner product is zero.
Exactly, you are right. You are right. The product of G alpha with itself will be zero, right?
So how is it non-degenerate?
Because the product of G alpha with G minus alpha is non-zero.
So G alpha is there no positive definiteness? I see.
Okay.
This is
okay.
Just like a symplectic form.
Yeah. In the same way. So this inner product is the inner product of something in here. But if we identify this space with this one, having a non-degenerate inner product on T, then we can transfer the inner product on here to this space. And therefore, this makes sense. And the claim is that the Lie algebra of my parabolic P is of this form. This is again stems from the representation theory, because this lambda is the eigenweight of some P semi-invariant vector, this S, yeah? And it follows now from representation theory of reductive groups that the stabilizer of the line generated by S, this P, which contains P, is, is exactly of this form. Actually, P is the stabilizer of this divisor. Yeah. So this is the structure of the Lie algebra of P. And the unipotent radical has the Lie algebra of the following shape. So in this P, we have the Lie algebra of PU, which is just the direct sum of those root subspaces for which this product is strictly positive. While the Lie algebra of L is the direct sum of T with those of the root subspaces for which this inner product is zero. We can visualize this decomposition in the following picture. Let me draw a picture for you. So we have something.
Why we have this decomposition?
Well, again, as I say, this follows from the representation theory of reductive groups, because P is the stabilizer of the line generated by S. And this line, on this line, it acts by the eigenweight lambda. And from these two conditions, it follows that, yeah.
Well, you mean that B, the Borel subgroup B acting on...
Not just the Borel subgroup, because this section S...
is P stable?
Is P not stable? It is P semi-invariant. The line generated by S, is P stable. And actually, P is exactly the stabilizer of this line because P is the stabilizer of this divisor. Okay.
P is the stabilizer. So we can decompose the algebra P by the positive root under lambda, right?
Well, let me just draw a picture, and then maybe some questions will be clarified because the picture is self-explaining. So the picture is as follows. So we have this lambda. We have the orthogonal hyperplane to this lambda. Let me draw this hyperplane. Something like this. Well, here, maybe here. This is the hyperplane orthogonal to lambda. And this will be my lambda. Let me again put it by thin arrow. This will be my lambda. Excuse me. I should delete here. Yeah. This is my lambda. This is the orthogonal hyperplane. And also we have roots. We have roots. Well, maybe roots will be in blue. For instance, this one. Maybe this one. Of course, we have opposite roots in all cases. This will be the opposite root to that one. And this will be the opposite root to this root. Yeah.
Professor, and since a side question, since lambda and the root alpha both lies in the dual space, so why don't we define the bilinear product in the dual space?
We define the bilinear product in the dual space by transferring it from here, because we have a product on here, and it is non-degenerate. Since it is non-degenerate, by means of this inner product, we can identify this space with this one and transfer the inner product from here to here. This is how we define this.
Oh, yes, I know. Oh.
Okay. Well, so we have roots. Some of them are above this hyperplane. Some of them are below this hyperplane. And some of them are in this hyperplane. For instance, these two opposite roots are in this hyperplane. Yeah? Maybe this should be made longer, like this. So all these are roots. Let me put arrows here. These are roots. And now, the roots corresponding to the unipotent radical, these roots, are above this hyperplane, are exactly the roots above this hyperplane. So what is above this hyperplane corresponds to the unipotent radical of P. And the roots corresponding to the Levy subgroup, these roots, are on this hyperplane. So the roots on this hyperplane correspond to L. So this is a picture of how all things look like. Okay? In particular, all roots corresponding to PU are positive roots. But not all positive roots correspond to PU. Some of positive roots correspond to L. For instance, we may take another hyperplane which separates these four roots from these four roots. Then these four roots will be positive, and these four roots will be negative. And some of positive roots belong to the Levy subgroup. Also, the negative of them belong to the Levy subgroup. But all roots belonging to PU are, of course, positive. So this is the visualization of this 2D composition, of these 3D compositions. Okay? Now,
sorry.
yeah.
So I have a question.
Yeah.
So now this inner product, you have no positive definite, right?
No, it is not positive definite because it makes no sense to speak about positive definity here.
Okay.
It is not taking real numbers. It is taking values in an algebraically closed field, say in complex numbers.
Right. So how to understand this greater or greater equal?
Yes, actually, you are right. So the point is that actually this product is positive definite on the lattice of characters. Yeah, maybe it is important to mention this. Maybe, yeah. Let me thank you for this comment. It is indeed, otherwise it is confusing. Let me say do it like this. I will move it to somewhere below. This I will move back.
So I think this is we just choose a hyperplane that splits the root.
Excuse me. Let me answer the previous question. So maybe the fourth property, which is important to mention, is that this inner product. Excuse me. This inner product is real valued even rational valued. So you may even prove that the inner product as we defined is rational valued and positive definite on the character lattice of T, which can be viewed as a sublattice in T star, which is identified with T by this inner product. Yes, this is an important observation. Thank you for this comment. And therefore, this inequalities make sense. Okay?
Okay, thanks.
Okay, so now I can move it back somewhere here.
By the way, so what is?
I think like this is okay. Okay. Yeah.
So what is the restriction on this lambda t? Yes, because if the span of this lambda t with the coefficients in the field K is T star, right?
Because, say it again. Because of what? I didn't understand.
He means that T star is lambda t tensor the field K.
Yeah. T star, yeah. If this was the question, then yes, T star is lambda of T tensor with K over Z.
Okay, so it is reasonable to think that this is real valued on this.
It is even rational values on this lattice. Okay, excuse me.
Okay, thanks.
Professor, since lambda t is a lattice, can we say that it is Z valued, not only Q valued?
Let me think. I think that you are right, but well, yes, I think that you are right. But just for safety, let me keep Q here. I think that it is even Z valued. Well, I will think a couple of minutes about it after the lecture, and then I will correct this Q just to make the statement more precise. Okay, I think that you are right. Just I don't want to prove it, of course. I will not comment on the proof. I gave you a reference for all these kind of things, and I won't elaborate on this more. But I think that here you are right about z value. Well, let's go further. Let's proceed with the proof. So we have the section S, which is a p semi-invariant vector in the space of eigenweight lambda. This means in particular, maybe let me just to separate it from what was before, let me mark it as the fourth step in the proof. So if we take our section S, and if we apply any element in the Lie algebra to S, then what will we get? If this psi belongs to the maximal torus T, then of course this section S will be multiplied by the value of lambda at psi. But if psi belongs to some of the root subspaces, to one of the root subspaces, then we'll get 0 here. Just because not to all root subspaces, but to those root subspaces sitting in the Lie algebra of my parabolic. This is just because the section S is p semi-invariant. So if you are taking any element from the Lie algebra of parabolic, then the action of this element should multiply S by some scalar. If psi is in the maximal torus, then this scalar will be just the value of the weight lambda on psi. But if psi is in the root subspace corresponding to some root lambda, to some root alpha belonging to the Lie algebra of P, then the exponential of this psi will be a unipotent element in P, in the group P. And the characters, each character of P is identically 1 on unipotent elements. So unipotent elements, unipotent subgroups have no non-trivial characters. So on the group level, the respective group element will preserve S. And on the Lie algebra level, the respective element will annihilate S. So I explained these two formula here. And now we can conclude, therefore, we can conclude that phi of x can be identified with an element in the following affine subspaces: lambda plus the Lie algebra of Pu for any x in the open B chart. This stems from what was written before. Let me look at the previous page. So how we define this phi of x? It is a linear function in psi given by the following formula. Now, if psi belongs to a root subspace in P, then this value will be 0. So the numerator will be 0. If psi belongs to G alpha, with G alpha in the Lie algebra of P, then this will be 0. And if psi belongs to the maximal torus T, to the Lie algebra of the maximal torus, then this value will be just lambda of psi, because we have lambda of psi times S in the numerator and S in the denominator. They will cancel. So we'll just get this lambda of psi. Okay? This linear function takes this value on the maximal torus and 0 values on here. If we identify this linear function with an element in G by this identification, then this element LG will be orthogonal to all these root subspaces. In view of this property, the orthogonal complement of all root subspaces in here will be just the root subspaces in PU. Because if we have a root subspace in P, then the only root subspace non-orthogonal to it is the root subspace corresponding to the opposite root. Yeah. If G alpha is this one, then we have to take this root subspace. If G alpha is this one, then we have to take this root subspace. But if we want to have a vector orthogonal to all root subspaces in P, to all root subspaces here, 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 and here, then we can get only this root subspace corresponding to PU. And this condition on T says that the projection to T of this vector will be exactly this lambda. So we have this property. In other words, let me turn to the next page. In other words, our map phi sends the open B chart to this space, viewed as a subspace in G identified with G star.
Lambda 加 PU, the plus of lambda and PU is seen as the sum of subspace, right?
I mean that lambda here is a fixed vector.
Oh,
in
it
the
is a
algebra of
translation
T.
of subspace. You mean?
Yes, it is a translation of this subspace. Exactly. It is not a vector subspace in here. It is an affine subspace. It is a translation of this vector subspace, right? And this map is P equivariant. Recall that this map is P equivariant. Okay. Now I need the following claim. This shifted subspace, lambda plus the Lie algebra of PU, is a single P orbit, is the adjoint P orbit of the vector lambda. And it is isomorphic to the quotient of P over L. Let us prove this claim.
The quotient of P over L is not a subgroup, I think.
Yes, it is a homogeneous space. It is not a subgroup. It is a homogeneous space. Proof of the claim. Well, first of all, observe. So recall that we view lambda as a vector in T by this identification, yeah? And we can consider the adjoint operator of this vector lambda. Now, let me shift it, I think. Better to shift it to the next slide like this, yeah? Well, the adjoint operator of this lambda, yeah.
I still don't understand why the image of phi lies in this affine subspace. I mean,
well, this follows from this formula and from this formula for inner products. Maybe.
I'm just asking why there exists inner product in the action of phi x on psi.
Why what?
Why there is inner product when we apply phi x to psi?
Here it is not an inner product. Here it is a pairing.
Yes, this is not inner product. So I was.
But I mean, let me say, I mean, if you identify G star with G via this inner product, then this pairing will become an inner product.
So you are using the dual. Oh, I see.
Exactly. So if you consider this as a vector in the dual space, then you have to take the pairing. But if you consider this as a vector in the same space, then this pairing will be replaced with the inner product. Okay? Maybe I will, it is better to do like this. If you still have questions about what was discussed previously, then maybe we could discuss it after the end of the lecture, because otherwise I will not finish the proof. I want to finish the proof today. Let me go further with the proof, and after the proof, I can discuss, I can answer all remaining questions, should you have any. Okay? So, let's come back to the proof of the claim. So we have this adjoint operator of lambda. What can we say about this adjoint operator? Well, it vanishes on T because lambda itself belongs to T and T is commutative. And if you apply this adjoint operator to any root subspace, say G alpha, then you will get just the scalar operator. Just the multiplication with this product of alpha with lambda times the identity. This will be the action of this adjoint operator on G alpha. Because G alpha is an eigenspace for the action of T, and lambda belongs to T. Okay? So having these two formulae, we see immediately that if you commute the Lie algebra of L with lambda,
Sorry, Professor.
yeah.
And so, I mean, if S is P semi-invariant, then how is phi? Why is phi not constant? Because I mean, the psi acting on S is a multiple of S and does not belong to X.
Well, I mean, here it is constant at any point, but the ratio may depend. Well, I mean, how to say? It is constant at any point. This ratio for fixed psi, this is constant at any point, but the ratio may depend on X. There is no reason for this ratio not to depend on X, I mean.
Well, you just prove that the psi acting on S is lambda psi.
Well,
if it's just for psi in T, right? Not psi in others. So if psi is not in T, then it should depend on X. You mean this?
Oh, yes. Not only this. I mean, no. You are right. When you take psi in P, then of course this will be constant. But when you take psi not in P, then you don't know what happens here. So this formula applies only for psi in P. Both formula applies only for psi in P. But this formula defines as a linear function on the whole G. Okay? We don't know what happens outside P. What we can tell, only this thing. So this addition actually controls what happens outside P. This lambda controls what happens on P when psi is taken from P. This is this lambda. And when psi is taken outside P, then this addition controls this action. Okay, so let's come back to the proof of the claim. Now, these two formulae imply immediately that if you commute the Lie algebra of the Levy with lambda, then we get 0. And if you commute the Lie algebra of the unipotent radical, Pu, with lambda, then you get Pu itself. Just because Pu consists of those root subspaces for which this inner product is positive. So the adjoint operator of lambda acts in a non-degenerate way on each root subspace from Pu. And therefore, its action on Pu is non-degenerate. So we get the whole space. As for L consists of T on which the action is 0. And of those root subspaces for which this inner product is also 0. So the action of L is 0. So I explained these two equalities. Now, this implies, first of all, that this affine subspace lambda plus Pu is stable under the action both of Pu and of L. Because when you apply this to lambda, you do not get outside this space. And when you apply L or Pu to Pu, you still get into Pu, because it is an ideal in the Lie algebra of P. So since the Lie algebra of P acts on this affine subspace, the group P itself also acts on it. So we get an adjoint action of P on this shifted subspace lambda plus Pu. And the stabilizer of lambda in P is exactly L. Because L, of course, stabilizes. L stabilizes lambda in view of this formula. The Lie algebra of L annihilates lambda, therefore L stabilizes lambda. While the unipotent radical acts simply transitively. The stabilizer of P lambda in the unipotent radical is trivial, because the Lie algebra of unipotent radical, nothing of the Lie algebra of Pu annihilates lambda. So we have this, and this implies, in turn, that the adjoint orbit of lambda under P is the same as the adjoint orbit of lambda under Pu, because P is the product of Pu and L stabilizes lambda. And this adjoint orbit is isomorphic to Pu.
Since the stabilizer is L, we directly deduce that the orbit is isomorphic to the quotient space.
You may say, yes, you may say like this, that, yeah, the orbit is isomorphic to the quotient. This is exactly this statement. But I also want to prove that the orbit is the whole space itself. And for this reason, to this end, I argue as follows. So this orbit is isomorphic to Pu. And Pu as an algebraic variety is in fact just an affine space, because we have an exponential isomorphism. We have an exponential map from the Lie algebra of Pu to Pu. And since Pu is a unipotent group, this exponential map is an isomorphism. This is a property of unipotent groups. So on one side, we have that this orbit is isomorphic to this affine space, to this vector space or affine space, if you like. And on the other side, this orbit is contained, of course, in lambda plus Pu, which is again an affine space of the same dimension. But this implies that they have to coincide. Because, let me comment, because it is not possible to embed an affine space to itself as an open subset. If this orbit were smaller than this space, then this orbit would be an open subvariety in here of the same dimension. And actually, this open subvariety will be isomorphic to this space, that is to this space. So we would get an embedding of an affine space into itself, essentially, as an open subset. And this is not possible. For instance, because if such an embedding existed, then you could take a complementary divisor to this open subset in here. This complementary divisor is given by a single equation because the coordinate ring of the affine space is factorial, is a unique factorization domain. And the equation of this divisor, of this complementary divisor, would give us an invertible function on this open subset. But you know that there are no invertible functions on an affine space except constants. So such kind of non-trivial open embedding is not possible. And this proves this equality. Okay? So we have proved the claim. Yeah.
Yes, you have proved the claim.
Yeah.
Well, I still want to ask, why is the joint action of lambda is 0 on T and something like?
Why is the joint action of lambda 0 on T? Because lambda belongs to T, and T is commutative.
Oh, and the second line.
And the second line, this is because G sub alpha is an eigenspace.
G sub alpha is the eigenspace.
Yeah. And the eigenweight is lambda. When you apply this eigenweight to the eigenweight is alpha. When you apply this eigenweight to this vector lambda under these identifications of the dual space with the space itself, you will get this inner product. Okay. Okay, so we have proved the claim, and now we are close to finishing the proof of the theorem. Well, first of all, we have this map phi from x, y naught to this shifted subspace, and this shifted subspace is a single p orbit with stabilizer L, as this claim states. When we have a p equivariant map to a single orbit, then the source variety comes equipped with the structure of a fiber bundle over this orbit. So thus we have this map phi from x, y naught to lambda plus pu, which is isomorphic to p over L. And this immediately implies that x, y naught is a fiber bundle over this orbit, p over L, with the fiber z. So z here is just the inverse image of lambda, a point in here with stabilizer L. Okay, so we have proved. Excuse me, the first statement of the theorem. And now it is more or less easy to prove the remaining statements. Let's do it. First, this will be the, I guess, the fifth step. the fifth step of the proof. So we have an open B orbit. In the open B chart, the open B orbit I denote like this, Y upper node. This implies that the variety Z contains the intersection of Y upper node with Z, which is exactly the open. Well, maybe I should add here that the Borel subgroup B has also the structure of a semi-direct product of PU with the intersection of B with L. So the Levy decomposition for P gives rise to the following decomposition for B, because B is inside P. Okay? And now from what we have proved here, and from this decomposition, we get that the intersection of Y naught with Z is exactly the open B intersect with L orbit in Z. Which of course implies that Z is spherical for the action of L, because B intersect with L is a Borel subgroup in L. So we have proved part of this. We have proved part of this second property. Z is affine because it is closed in affine. This chart is affine and Z is closed in this. Therefore, Z is affine and also Z is spherical. This we didn't prove yet, but we'll do it soon. Now we turn to the third property.
So what about the normality of this Z?
Well, X was normal. This guy is also normal because it is open in X. And in view of this direct product decomposition, if X, Y naught is normal, this is just an affine space. Then this should be also normal. Okay?
Okay.
Okay. So for any B semi-invariant function, so maybe again, let me put it as the sixth step, just to put some structure in the proof. For any B semi-invariant rational function, say f on X, of some eigenweight lambda, its restriction, say f prime, let it be the restriction of f to z, will be also a semi-invariant function on z with respect to this Borel subgroup B intersect with L of the same eigenweight. This is again because of this structure of the open chart, because this guy is isomorphic to this direct product. And if you consider B semi-invariant functions, they should be invariant under the unipotent radical, under PU. So they are uniquely determined by their restriction on Z. And the restriction functions should be semi-invariant with respect to the remaining part of the Borel subgroup, with respect to this, of the same eigenweight, because the maximal torus T sits in here. It acts on Z. And conversely,
well, the first implication in 6 is because B acting transitively on the fibers, right? Because B contains PU.
Yes, PU just permutes the fibers. Yeah. So if you take any semi-invariant function on Z with respect to the Borel subgroup in L, then it can be uniquely extended to a semi-invariant function on X, or on the open B chart, if you like, by the following formula. You just take f on the product of u with z equal to f prime of z for any u in pu and z in big Z. So this means that essentially B semi-invariant functions are the same on X and on Z. They correspond one-to-one. They are in a one-to-one correspondence given by restriction of functions to Z. And this implies, of course, that the weight lattices are the same. So we have proved that the weight lattices are the same. Now let's turn to the colored data. So we are very close to the end of the proof, but let me still say, we still have to say something. So let me turn to the next page, and this will be the 7th step, right? Yeah, 7th step. So let us observe that if you take a B-stable prime divisor in X, B-stable prime divisor in X.
Hey, Professor, we prove that Z is affine. I don't think so.
Yes, we proved that Z is affine because Z is a closed subset in the affine open B chart. So if we take
closed in affine. Oh, I see.
Closed in affine, yeah, closed in affine. So if we take a B-stable prime divisor in X, then it intersects the open B chart if and only if it does not contain the orbit Y, the closed orbit Y, because the open B chart is obtained exactly by removing all prime divisors B stable which do not contain Y. So if the divisor intersects the open B chart, it is not removed, it contains Y. This is this equivalence. And this intersection, again, in view of the structure of the open B chart, excuse me, this intersection is of the following form. It is a product of PU with the intersection of D with Z. And this intersection, let me denote it by D prime, is a prime B intersect with L stable divisor in Z. It is stable under the Borel subgroup in L. And conversely, any B intersect with L stable prime divisor in Z is of this form. If we have such a divisor, then we may take D equal to the closure of the PU span of D prime. This will be a divisor in X. It is B stable.
Well, why should this be a divisor? Because
it is a product. Well, because of this product structure. Because of this product structure.
XY0 is a trivial bundle. I see.
Well, I would even say it is a direct product. XY0 is this direct product. And if you have a divisor in here, which is stable under B, B includes PU, then of course this divisor should be of the form PU cross something in here. And the dimension, the codimension will be preserved, yeah, because we have the whole factor here. We take the whole factor here. So any divisor in this product is, which is B stable, is a product of this guy and some divisor in here. So everything stems from this product decomposition. And conversely, any divisor d prime in Z, which is stable under this Borel subgroup in L, if we take the PU span of this divisor and close it up, then we get a B-stable divisor in X intersecting the open B chart and containing Y, therefore. So, and even more, the more so, the vectors in the dual weight lattice, VD bar and VD prime bar, are the same. In particular, this implies that the divisor D contains the divisor D constructed in this form how to say, the divisor D constructed by this span, by this PU span, it intersects the open B chart, therefore it contains Y. And this implies in turn that D prime contains Y intersect with Z. So what do we have? We have proved that any prime divisor in Z, which is stable under the Borel subgroup, contains this subset, this closed subset, this closed L-stable subset. This means, let me write it here, this means that this intersection subset is the unique closed L orbit in Z. The unique closed L orbit in Z. If it were not a single L orbit, then well, it is L stable. This subset is L stable. It is a closure of some L orbit. But if it were not a single L orbit, then there would be some smaller L orbits on the boundary. But it follows from the classification of spherical varieties by means of colored data that an orbit is uniquely determined by the set of divisors, of B-stable divisors containing this orbit. Yeah, because this data is encoded in its colored column. And here we have that the orbit, the open orbit in here is contained in all divisors stable under the Borel subgroup. Yeah, so all these divisors contain this orbit. So there cannot be any other smaller orbit, because then there should be more divisors which contain this smaller orbit. So this proves that this is a unique closed orbit. And we finally proved the second property in a whole, and also we proved this, and it remains to explain these two equalities. But it is already easy because we already discussed the structure of B stable and B intersect with L stable divisors. So we get that the cone corresponding to this closed orbit in Z is spanned by all these vectors VD prime bar corresponding to D prime bar in Z, which are B intersect with L stable. Okay? But these vectors are the same as the vectors corresponding to the divisors D, which intersect the open B chart, which contains Y, such that D B stable and containing Y. And the cone spanned by the vectors VD bar of this form is exactly the cone. So let me write it like this. This is the cone spanned by these vectors, and this is exactly the cone C sub y. And finally, for the colors, we get the following: that D prime is a color containing this orbit in Z, if and only if it is not stable under L. Because D was a B intersect with L stable divisor, and if it is not L stable, then it is a color. But this condition is equivalent to saying that the divisor D, which is obtained from D prime by the PU span, is not stabilized, not preserved by P. And this is exactly the condition here. This is exactly the condition here. So we have described the colors in Z as those colors, they are in a bijection with those colors in X, which contain Y and which are not stable under P. Finally, we have proved all statements, and this is the end of the proof of the theorem. Sorry that I have taken your time again, but this is because I answered questions. Otherwise, I would never finish the proof. Now the proof is over. So we have proved this local structure theorem. Maybe to conclude, yeah, maybe no. I think I will continue on the next lecture on Monday, and now I will stop. I'm ready to answer your questions if there are any questions left.
I want to see the last 3 pages. I have to get some screenshots.
Let's turn to these pages. So this one, previous one,
last one.
Last but one? You mean this one?
No. I mean the previous one. Yes.
This one. Okay.
Yes. I mean you conclude that the image of lambda is the whole lambda plus pu, right?
Yes. The orbit of lambda is the whole lambda plus pu. Yeah.
So since the image of phi is init, it must. I mean it is a single orbit. I see.
Yes. So what I want to prove that this shifted subspace is a single orbit. Exactly.
I want to see the next page, and I will take a screenshot. Yes, and next page. And next page. Well, I have a question about the decomposition of the Lie algebra of P.
This one?
Yes. Well, why do we sum non-negative or only some non-negative roots? I think well some time ago, I mean the decomposition of arbitrary reductive group is we sum over all positive all roots and the positive
yes. Well, if you write G here, then you get the decomposition over all roots. But P is a subalgebra in G distinguished by this condition.
Why distinguished by this condition?
Well, as I said, well, I brushed it under the carpet. I didn't prove it. I just told you that this stems from the representation theory. It takes some time to explain. If you know the representation theory of reductive groups, it is more or less obvious for you because essentially it stems from the SL2 theory, from the theory of representations of SL2, because
Well,
so,
does the decomposition stems from that S? This is a representation of highest weight lambda. I mean,
exactly. So this P is the stabilizer of some vector of highest weight lambda. Not vector, but the whole line. This P is the stabilizer of the line spanned by the highest weight vector of highest weight lambda. And this is the reason, actually.
Well, the reason is P stabilize that line, not because that line is the highest weight. I mean, the highest weight is just stabilized by the Borel subgroup.
Exactly, and this is a bigger subgroup. This is a bigger subgroup. So the highest weight line is stabilized by the Borel subgroup, but it may be stabilized by a bigger subgroup. And I take for P the whole stabilizer, because I claim that here P is the stabilizer of the line spanned by S, because the divisor of S is not only P stable, it is P stable, but even the more so. P is exactly the stabilizer of this divisor. This is because of this property. P can be defined like this. It is the common stabilizer of all D's not containing Y. And the divisor delta is just the sum of these D's. So P is exactly the stabilizer of delta. And therefore, it is exactly the stabilizer of this line.
I mean, delta is the sum of D, so P stabilizes delta. I mean, this is right, but why P is precisely the stabilizer? I mean,
let me repeat again. So let me repeat again why P is precisely the stabilizer. Because what is P? P is this guy. P is the intersection of the stabilizers of all D's which are B-stable and not containing Y.
Yes.
And now what is delta? Delta is the sum of these D's.
Yes, so if some element perturbs the perturbs D but does not keep D,
no, they cannot be permuted. This we already discussed. Because anyway, all these D's are stabilized by the Borel subgroup, right? All
yes.
these D's are stabilized by the Borel subgroup. Therefore, the precise stabilizer of this divisor is bigger or equal than B. It is a parabolic subgroup, some parabolic subgroup.
Yes.
And any parabolic subgroup is connected. So if a parabolic subgroup stabilizes something finite, it cannot permute the element of this finite set. It has only to preserve each element, because it is connected.
Connected means that I mean also for any single point the orbit of the stabilizer should lies inside a whole divisor. So it must keep the divisor.
Yes. I mean, if you apply P to any of these divisors, you will get into the union of these divisors. But P is connected or irreducible, if you like. So if you apply P to any of these divisors, you will get something irreducible. Something irreducible which contains given D and lies in the union of all D's. This means that it is just D itself. Okay?
Oh, I see. Thanks.
Okay. You are welcome. So, more questions? feel free to ask me by email if you have any questions later. I usually repeat this, so you can do this. Are there more questions or comments? Well, so today we have proved this local structure theorem, which explains how spherical varieties look like locally. And on the next lecture, on Monday, we shall elaborate more on these structures, on this local structure. We shall introduce a nice subclass of spherical varieties, whose local structure is even better understood than in the general case. And maybe we shall discuss some applications of this local structure theorem to the geometry of spherical varieties. This is my plan for the 23rd lecture, last but one, on next Monday. And I hope to see you all next Monday. So if there are no more questions, let me then stop sharing. And I say goodbye to all of you. See you on Monday. Bye-bye.